Good morning, everybody in the Americas. Good afternoon and good evening in Europe, Middle East, Africa, Asia, and Pacific. I am Ron Gupta, President of PanIIT USA. PanIIT is an umbrella organization of all IITs. There are 23 IITs in India at the moment, and 2 outside India were inaugurated this year. We have done numerous webinars and conferences. This conference will be on future of computing. I'm sure all of you are interested in the quantum leap into the computers. You are perhaps being watched by as many as 50,000 alumni that live in the US. We have 500,000 alumni worldwide. Let me introduce at this time Witty Bindra. Witty is a board member of PanIIT. In fact, an eminent board member. He has previously been board member, president, and chair, and has ran many of the conferences. He's a graduate of IIT Delhi. He worked in New Zealand, and then since then he's been working in the US, in Houston, with various companies. At this time, I would like Witty to take over the webinar. I urge all the participants to not only enjoy it, but also write down any comments that you have and send those to our Executive Director, Swati Deshpande. Thank you and good luck, Witty.
Thank you, Ron. Thank you for the introduction. I appreciate that. And hello, all. As Ron said, I am a prominent alumnus and board member of PanIIT USA. On a professional level, I work for Kyndryl and IBM spinoff, and I lead the Microsoft Global Alliances for the Europe, Middle East, Africa, and the APAC regions. And I am the strategic advisor for Kyndryl India, based out of Houston. So we are here today at the forefront of technological innovation. Quantum computing, once a realm of theoretical physics, is now rapidly becoming a tangible reality. We are honored to join by 3 leading experts in quantum computing. Their expertise spans from theoretical foundation to practical applications. They will provide us with invaluable insights into the current state and future potential of this revolutionary technology. Our first eminent panelist is Professor Anil Prabhakar. Anil is a distinguished faculty member at the Department of Electrical Engineering, IIT Madras, where he has served since 2002. He earned his PhD in 1997 from Carnegie Mellon, focusing on non-linear spin wave optical interactions. A leading figure in quantum technologies, Anil is the principal investigator of the Center of Excellence on Quantum Information, Communication, and Computing. His entrepreneurial spirit is evident of his co-founding of QNU Labs and Qualcomm's, both IIT Madras incubated companies dedicated to translating quantum research into practical applications. He also spearheads the Metro Area Quantum Access Networks project. Anil is actively engaged in shaping the future of quantum technology through his roles in national and international scientific and standardization committees. He is a member of several journal editorial boards and chairs the task force on quantum communication for the Quad countries. With over 50 research publications, a co-authored book on spin waves, and 18 patents, Anil's contribution to the field are substantial. Our second panelist is Dr. Abhinav Kandala. Abhinav is a leading experimental physicist and principal research scientist at IBM Research. He heads the Quantum Capabilities and Demonstrations team, which is focused on developing tools for large-scale quantum computing and exploring the boundaries of quantum computation. Abhinav's research has spanned from fundamental qubit control and characterization to the practical applications of quantum computers. His pioneering work demonstrating the potential of near-term quantum processors to deliver useful results culminated in IBM's groundbreaking quantum utility experiment in 2023. A recognized expert in the field, Abhinav was named one of the MIT Technology Review's 35 Innovators Under 35 in 2019 and received the Young Alumni Achiever Award from IIT Bombay in 2024. He holds a bachelor's degree in engineering physics from IIT Bombay and PhD in physics from Penn State University. And finally, our third panelist, Dr. Rajeev Malik. Rajeev is a key figure in the global push towards quantum computing, a program director for system development and deployment at IBM He spearheads a team dedicated to developing and testing the next generation of IBM's quantum systems. This includes creating these cutting-edge technologies and their deployment worldwide. Rajeev plays a vital role in driving his organization's quantum system roadmap. This strategic plan ensures that a global network of researchers, educators, developers, and enterprise clients can access state-of-the-art quantum computing infrastructure. This allows them to explore innovative applications and push the boundaries toward achieving significant quantum advantage, where quantum computers outperform even the most powerful classical computers. His leadership extends beyond the development stage. Rajeev's teams manage IBM entire fleet of quantum systems, which span data centers and client sites worldwide, including US, Germany, Japan, and Canada. The vast network of quantum computers is a testament of Rajeev's expertise in scaling and deploying these complex technologies. He brings a wealth of experience to his role. Before leading the quantum systems team, he headed teams responsible for cloud infrastructure development for quantum services, technology development for high-end semiconductor microprocessors, and foundry interface management. He earned his PhD from University of Michigan and a BTech from IIT Bombay. So please join me in welcoming our esteemed panelist. Rajeev, I hand over to you.
Thanks, Witty. Hello, everyone. Ron said good morning, good afternoon, good evening. So what we're going to do today, I'm going to share our slides in a second. There's the three of us over the next hour or so. We'll walk you through some of the different aspects of quantum computing, a little bit of an introduction, all the way through how they're being used today and what's to come in the future. We want to keep the session quite interactive. We certainly have a bunch of presentation slides for you to see, but feel free to type in the Q&A box whenever you have questions, and we'll be happy to answer them as we go along. So I am gonna do, would somebody mind, Witty or Swati, just allow sharing? I'm not able to share. If you can do that, I'll start by sharing slides.
Yeah.
Perfect.
And as you're working on slides, for any question answers, please use Q&A box. Don't send the question in the chat window. Just use the Q&A area. Thank you.
All right. Hopefully everybody can see the slides. So this is kind of our agenda for today. We'll talk a little bit about what quantum is, a little bit of the history, and what are some of the real world problems being looked at with these computers. Talk a little bit about workforce development and training, touch upon some of the investments worldwide, including at NQM, where Anil's playing a very key role in India. Some of our challenges, and then what can you do next? Hopefully, some of you may already know about quantum computing. Some kick it off today, and then you can kind of build off it. So, why quantum computers? I'll give a couple of intro slides and turn it over to Anil. And he'll walk through a little bit of the details on what are quantum computers. But really, quantum computing came about because we know there are certain problems today that classical computers are not in a position to handle well, whether it's too slow, they're not accurate enough, or they're just not able to solve. That's what's kind of in this hard problems bucket. And what we've seen, and you'll see it over the course of this presentation, that quantum computers have the capability of taking a subset of those problems and being extremely efficient at them, right? So the goal is not for quantum computers to replace everything that classical computers are doing, but take a subset of those problems and which really high level involve simulating quantum mechanics and be able to, in conjunction with classical computers, be able to solve those a lot more efficiently, faster, with a lot more accuracy. And effectively, this is where we see computing starting to branch, right? The typical, you look at it over the last century or so, we've gone from mechanical computing elements to vacuum tubes to semiconductor-based transistors and everything that's been happening in our world around us in computing. And we really believe this is a true branch where there is the possibility of doing things that classical computers are not able to do. And with that, I'm going to turn it over to Anil, who'll give you a very brief idea about everything quantum and hopefully address what some of you may have heard and address it in the context of NQM as well. So Anil, all yours.
Thanks, Rajeev. I mean, since we have the NQM slide out here, let me just start by talking about the National Quantum Mission in India. This mission mirrors what has been happening in other countries around the world, whether it is in the US or UK or Australia, Europe. Everybody has similar verticals or horizontals in this case of quantum computing, quantum communication, quantum sensing, and quantum materials. Some people might say quantum information and so on. But in the Indian National Quantum Mission, this is how we have broken it up. And today we are largely talking about the first row on quantum computing. But I like to differentiate between quantum communication and quantum computing. I mean, one of them deals with securing information that is in transit, which is quantum communication. And quantum computing, as Rajeev just mentioned, is more about solving some subset of NP-hard problems by trying to mimic quantum atoms, I would say, or quantum particles. The way they do it, and mostly today, is through superconducting qubits. Those are what we call artificial atoms. But at the same time, there are large teams of people who are working on atoms and ions and trying to manipulate them. There are people who work on photonics. Photonic qubits is something that has been around for much longer. And semiconductor qubits themselves, where companies like Intel would try to use dopant atoms in a semiconductor and treat it as a qubit, right? So our national mission has some simple goals, 2 bullet points: build somewhere between 50 to 1,000 qubits and secure communications for 2,000 kilometers. And if you have a question about why it's such a wide range from 50 to 1,000, it's because there are so many technologies and not all of them scale equally well, right? Rajeev, do you want to just go to the next slide?
Sure.
Right. So this is more of a introductory slide for people who are curious about what we mean by quantum computing. In classical computing, we are aware that bits are binary; they're either 0 or 1. In this little picture, what we call the block Poincare sphere, you'll see the 0 on the north pole and 1 on the south pole. And a qubit can reside anywhere on the sphere, right? And now you immediately understand that a qubit can take on many values. And to represent every point on the sphere, we use the complex notation, or we use the two angles theta and phi that are marked with respect to the z-axis and the x-axis, respectively. Right? What really makes quantum computing different from classical computing are two properties. One is superposition, that is a qubit or a particle, a quantum particle, would be in a superposition of the states 0 and 1, and that would be along the x-axis or along the y-axis or anywhere on the equatorial plane. And if you make a measurement, then you get a probability of being in either 0 or 1. And if you're on the equatorial plane, it should be obvious that you will get a probability of half of being a 0 or half of being 1. The other property, which is more curious and is hard to explain with one sphere, is the property of entanglement. You need to have two particles to be entangled. So you can't do it on one Bloch sphere. And of course, this idea of a single Bloch sphere starts losing its importance as you go to many more qubits. But entanglement is what Einstein called spooky action at a distance, where two particles that began together. For example, we have learned that electrons in the s orbital of a hydrogen atom would have spin up and spin down. If you separate them out, they will still continue to be spin up and spin down. You just don't know which one is up and which one is down, and vice versa. And to be able to do something like this today with artificial atoms is itself a remarkable technology, and it's a very exciting time to be part of this. Rajeev, next slide. Yeah, so this one is what I call the quantum zoo. Lots of people trying many different things, and it scales differently. Some of these work and some of these scale, and they don't all happen together. I think what will happen is that some of these technologies which are in the research area will move towards translation, and they've already begun. You'll see announcements happening continuously with atoms and ions. Recently, there were large ones with linear optics, and then with superconductors, of course. And we are all expecting that quantum dots will also appear soon enough, right? So these are all different technologies that are in place. And the question that one has to ask is, how do you know which one is going to succeed? And what is this about? Can you go to the next slide, Rajeev? Yeah, just go to the next one. So there is a criterion, right? And this was initiated 25 years ago, actually. In January, it will be 25. It's called the DiVincenzo criterion. And it tells you that if you want to compare all these things, you have to look at certain properties of lifetime. How long do these things last? How well do they connect? What is the fidelity? That is, if I do 2 plus 2, do I get 4 or do I get 3.999 and 4.001 with some probability? How well do they scale? Can you build a large quantum computer? Maybe you can work with a few of these, but you can't scale them, right? So this sort of table allows us to understand where we are going. And I have marked out a few of them in blue where a lot of work is happening. There is some work happening on the topological qubits, but we don't have one qubit yet. So I think there is still some time to get that, but people are working hard on that. Rajeev? Right. And this one actually is, to set the context, if you start looking at the companies, you'll see that it's color-coded a little bit out here, trying to tell you that different people are talking of different things. IBM, Google, D-Wave, Rigetti are all talking superconducting qubits. Intel is spin qubits. So you can't really very easily compare apples and oranges. And in fact, to cure the pitch even more, many times people are talking about circuits, the way we do digital circuits, and other times people are talking about annealers, which are a whole different beast altogether. So one has to really be careful when you get into this space to understand what people are talking about. Right.
So I'm sorry, Anil, to interrupt. I'm getting a lot of questions, so I'm not sure.
Okay.
Do you want me to ask
Yeah,
few
yeah.
of them?
Let's do the questions.
Okay, so the first one is, how do you see quantum computing integrating with classical semiconductor-based systems in the near future? Are there specific areas within semiconductor technology where quantum computing can provide a significant advantage or enhancement?
Well, why don't we ask Abhinav to take that? Abhinav, do you want to take that?
Yeah, absolutely. And maybe we can revisit this as we
Yeah.
offer some more context for things. But yeah, we're seeing increasing examples. I think will be slides specifically talking about this. So let me not steal that thunder. Just hold on and we'll get to that.
Perfect. And that
Okay.
second quick one is, what materials are quantum computers made of? Are they silicon-based?
No, so you'll see the technologies here. There's what I call superconducting qubits. So the Josephson junctions. Or if you're looking at ion traps, then they are actually different types of ions. They could be different types of rare earth ions, erbium, ytterbium, and so on. The spin qubits are semiconductor based. Photons are, of course, photons are not semiconductors. Topological insulators are still a search. People are still searching for different types of topological insulators. It's a theoretical idea, but we haven't measured them yet.
And that one quick was, how many qubits have been built so far?
Well, it depends on the time of the day and the direction of the wind. But I think we're probably in the hundreds. I think, and it's not just, one has to be careful about this because the superconducting qubits, of course, IBM themselves have demonstrated hundreds and even taken it up to 1,000, but they're a little noisy. If you look at ion traps, they're not as noisy, but they're very slow and they're much fewer in number. So there's no single answer to that, but you can imagine somewhere in the hundreds is a good number to pick today. And we are expecting, actually the next slide, Rajeev, will show that graph, right? So you'll see the logical qubits that you need. You need about 100 logical qubits. Today we have 100 noisy qubits. So you multiply that by a factor of 100 maybe.
100, yeah.
Right. And then you'll get an understanding of how many qubits we are at today.
Great. Yeah.
Just to add to Anil, what Anil said to that question, right? There really are, and you'll see it later on in the presentation, about this concept of qubit count is a very, call it, exciting number to quote, but there's so much more than just number of qubits. I think Anil was mentioning that as well, and I think Abhinav will as well. The quality of the qubits matters a lot. And Abhinav, hopefully you'll talk a little bit about the differentiation. I think Anil referred to it of logical versus actual physical qubit count, and that I think will help a lot of people as well.
Right. Thank you.
All right, Anil, all yours.
There are a few questions I just saw in a Q&A about, when will you use it and when will government use it and so on. And I think this is sort of Gartner's 2018 roadmap. And it kind of tells you where we are expecting to see changes happening first: optimization, finance, machine learning, and hybrid algorithms, where you use a combination of classical and quantum machine learning. And then you get into the higher levels of drug design and logistics. And finally, of course, the holy grail is to break everybody's password. But I think that's very far away from happening. So we can be safe.
Yeah. Thank you.
Yeah, so these are just some images, right? And a lot of people see these images and it looks very nice. Actually, the QPU, as we call it, analogous to a CPU, is a small chip that will sit at the bottom of these large refrigerators. Everybody who's working in these areas will have one of these refrigerators, one or more of these refrigerators. And it takes the temperature down from room temperature down to a few millikelvin, something like the temperature of outer space, right? And that's one of the reasons it's easy to understand this, is because we are trying to leverage of quantum mechanics, which becomes noisy if you talk to the environment. And so you want to isolate it and cool it down, temperature being a measure of the amount of noise or entropy. So you cool it down a lot, right? But yeah, as I mentioned earlier, the annealers, D-Wave will say they have 5,000 and Quantinuum will say they have 150 qubits in an ion trap. And these are all different technologies, so it's really not good to compare them, right? I think in this one, I had IBM at 400 qubits. I think that maybe this was a couple of years ago. Yeah. Rajiv, the next slide. And this was a photonics one that came out from China. And this was an amazing, I show this to a lot of my students and say, imagine little minions as graduate students aligning everything up together. And you have to get them all aligned to get this optics to travel correctly down this crisscross array. So that's a bit of a challenge. And that is one of the reasons that scalability of linear optics has not really taken off. But with this demonstration, I think there is some ideas that have come out that says that maybe it's a path to a scalable quantum computer. So one has to wait and watch. I think maybe I'm done, Rajiv. Is that right?
I think so. And then, I'm sure they'll be jumping in a lot. So
yeah,
I'll just, a couple of slides just on a timeline, right? So just to kind of talk a little bit about how long has this been around, and truly the idea of quantum computing, as Anil described it, really started back maybe about 50 years ago. So it's not that old, right? The bottom is really a scribble from, folks, IBM fellows, which was really the birth of quantum information theory. And then as you look at it over time, and about 30 years ago is where algorithms started to come about, to one thing that Anil referred to of breaking encryption, right? And then what's been happening over the last 20 or so years is where the hardware that can be used to start to demonstrate what was in theory has started to come about, right? And I would say within the last 10 years, it has really rocketed. On the top are what's happened in the industry. IBM's been a significant part of it, and those are some of the milestones at the bottom. But the reality is, we started to introduce a quantum computer out on the web about 8 years ago, and they're still available for free. And since then, there have been significant advances in the type of quantum computers that are available, the size, the quality, and that's what this chart shows, is the significant progress over the last many years, with the fairly aggressive roadmap that we have and others have as well, to be able to increase size to hundreds to thousands to tens of thousands of qubits, but also have those qubits be a much higher quality, and really get to a point where they can start to do something useful that Abhinav will talk about. This is a repeat, but just to kind of highlight all the various technologies that are in use today, and each really has their. So I grabbed this chart out of a McKinsey report that gives you a little bit also of investments that are going into some of these technologies, right? And what do they use? Photons use as a startup that really focuses on leveraging these for quantum computers. They use waveguides, superconducting qubits, as Anil talked about, and some of the others on how they get to the same effectively goal of being able to manipulate these qubits, and what's the kind of investment that's going in. So the fields are there. I think certainly we believe superconducting qubits have that nice sweet spot of scale, quality, and speed, because each has some advantages and disadvantages, but it's really where it is. But time's going to tell what's really going to succeed, or there could be multiple technologies going in for different types of workloads. So That's something we're all going to figure out. And that's what I was kind of talking about. This is really where how is a good way to look at it across technologies, because they are so different and they stress different things, is to look at scale, quality, and speed. There was a question on how some of these work. This gives you a sense, as Anil was explaining about fridges. So just a little bit more visual detail. There's this refrigerator that goes really cold. The processor, the QPU itself, sits inside this environment, and it keeps it in vacuum, so it minimizes the outside impact to those qubits that are super sensitive, because you're really looking at single transitions. There is a bunch of analog components here that deal with RF signals that go back and forth from this fridge. And then there are some classical computers that are actually connected in here to really have a workload that mostly is classical, and then there are some individual quantum elements. Now, hopefully this comes across well in Zoom for everybody. Hopefully your connection's good, but this gives you a sense of what happens, right? So you're on your laptop, you're sending your requests off the cloud, you have your electronics that sends RF signals to the quantum processor inside the fridge. You have your quantum interactions that go on inside, and then you have your return signal that kind of comes back through the electronics and gets converted to a digital signal that comes back to your computer. And again, visuals on the left is what Anil was showing you. On the right is kind of a nice view. There's these quantum computers, and we make them look nice as well. There's actually a working quantum computer at Rensselaer Polytechnic Institute and RPI. This actually physically sits inside a chapel. That's kind of cool and interesting. And then this is a quantum data center that has multiple quantum computers that clients have been using. With that, I'm going to switch it over to Abhinav, who's going to talk a little bit about how do you actually use a quantum computer to do real work.
Perfect. Thanks, Rajeev. Thanks, Anil, for really setting this up very nicely. And thanks, everyone, for joining. Maybe I just wanted to give some context for the motivations for this, and what were the visionary ideas that led to this field. And these are maybe quotes that some of you might have heard in other quantum computing panels and talks, but it's useful to reiterate some of these ideas. So even while quantum mechanics was being developed in the early 1900s, right? What was recognized very early on by Paul Dirac is that the equations that quantum mechanics gives us to describe quantum systems, these can describe very successfully lots of phenomena that we observe in quantum mechanics. But then if you try and take those laws, if you try and take those equations and you want to apply them exactly, solving that becomes very complicated. Okay. And this is because, for instance, if one has, say, a system with about 50 to 60 orbitals that one wants to represent in a problem, and this could be an example of something you do routinely in molecular simulation, having to represent the state of that system and manipulate it, that very easily requires memory that exceeds what one has on the world's most powerful supercomputers. That boundary lies at about 60 to 70 qubits already, or 60 to 70 quantum particles. So this is a very big challenge, right? That you can't exactly solve the equations that you have that describe these quantum systems. And now, if you go to the next slide, one can ask, well, are quantum systems very prevalent in our day-to-day? And it turns out absolutely. If we're trying to understand molecular dynamics for drug design, this essentially comes down to the interaction of molecules, and these are systems that are described by quantum mechanics. You've heard the term superconductors. These are materials where one can have current flow without any resistance. So this is great for any for not having things like energy loss in transmission lines and so on. But can one make these kinds of materials at room temperature? That requires us to understand the phenomena of high temperature superconductivity, which is also a huge challenge for simulating with classical computers. So this is another example of a very potentially practical quantum system. Trying to simulate reactions in batteries. This is the rage with everything we're doing with EV and so on, right? Trying to understand these materials better, trying to understand the reactions better, that also relies on the application of quantum mechanics, right? So we have these very important systems which are incredibly complex. Trying to solve them exactly is beyond what one can do with the world's most powerful supercomputers, and one really has to now rely either on approximate classical methods which don't solve this problem exactly, or one needs something else, right? And if you go to the next slide, this was one of the pioneering ideas from Richard Feynman, which is that we want to simulate the properties of some natural quantum systems, like the examples I just shared. But instead of relying on a classical computer, can we actually build another quantum system, one that we can program, we can control, we can manipulate to actually perform computations or simulations that lead to that lead to our understanding of properties of the kind of actual quantum systems we care about. So this was the idea. And to offer some more intuition for this, if we can go to the next slide. Right. What we have on the right is an example of a superconducting quantum chip. Okay, this is one with 7 qubits, and what I have is as a circle there is a superconducting transmon qubit. Okay, and these are basically, one can imagine these to be artificial atoms. One can use microwave design to essentially manipulate the quantum states of these circuits at very low temperatures. Okay, and the idea, if you can just hit through once again, is can we use networks of these artificial atoms to simulate the properties of say real atoms in a real molecule? Okay, that's the basic idea. And for instance, with these artificial atoms here, this is at a much larger scale than what one might have with a real molecule. So you can drive electrical signals, you can measure the state of these artificial atoms. So one has the ability to really manipulate, program, and control the way we would a regular computer. Okay, you can go to the next slide. Yeah. So the idea of trying to simulate other quantum systems, other quantum materials, this was one of the leading motivations for driving a lot of the interest in the early days of quantum computing. But then came this really amazing development from Peter Shor of Peter Shor's quantum algorithm for factoring, and this is basically if you have a very large number and you're asked to identify what its prime factors are, this is a problem on classical computers that for these sizes could take millions of years. And what Peter Shor showed, that if one built a quantum computer, this is a problem that could be solved in hours. And this problem, this factoring problem, is basically the basis of things like RSA encryption that was which was already alluded to by Anil. This obviously led to a lot of interest from intelligence agencies across the world, and really was a game changer in the context of the amount of funding that was driven into the field from the mid-90s onwards. And this has really been crucial. This development has been really crucial for supporting the kind of research that went into building these quantum computers. Okay, so this was about the mid-90s, and people have been trying to build quantum computers since then. And I want to give you some sense for why is this such a challenging task, right? We're 30 years approximately since Peter Shor's algorithm was first published. If you try and compare the errors that we have in a classical computer, in the building blocks in a transistor, and compare that to the building block of a quantum computer, the qubit, right? The error rates are larger by over 20 orders of magnitude. Okay, so what this means is we're trying to perform useful computations on these quantum computers. We want to perform certain operations, we want to program them, but we're just losing information very quickly. Okay, and this is an incredibly challenging task, and this is really why it's been this hard to actually build these systems. And then one can ask, well, okay, these quantum computers have these large errors, they're very noisy, but can they still perform computations that are useful? Can they still perform computations that are beyond the reach of the world's most powerful classical supercomputers? Right? That's one. The second is the grander vision of well, these errors exist, but there is a known theory, there is a known protocol for how we can correct these errors. Okay, and this is the theory of quantum error correction. And if one were to implement this, one would have what is referred to as a fault-tolerant quantum computer. And these are the kinds of quantum computers one needs to build to run something like Shor's factoring algorithm to break RSA encryption. Okay, and the basic idea here is there was a mention of what physical qubits are and what logical qubits are. These physical qubits have very large error rates, like much larger than what one typically deals with on classical computers. The idea is to delocalize that quantum information. So the information you have on one physical qubit, you can delocalize it across a larger network of physical qubits, so that when one has errors that appear locally, they're still slow enough that you can detect them and correct them and so on. So the information on a physical qubit, you encode on a larger network of those, and that then forms a logical qubit. And then one needs to do operations on those logical qubits and so on. But this would be how one could build an error-corrected, fault-tolerant quantum computer. Okay, so Shor's factoring algorithm happened in the mid-90s. Fast forward to 2016. Okay, there was a lot of research that happened in academic labs and national labs across the world. Then another very important pivot point was 2016, when this became technology that could be accessed by anyone, sitting anywhere with access to the internet, and this really was the beginning of really taking these kinds of very complex research grade devices and putting them up for public consumption, essentially, right? If what I have here is once again what I have here once again is a superconducting quantum chip. This one has these 5 squares. Each of those represent a superconducting transmon qubit. And this was just a device with 5 qubits. And there is absolutely nothing you can do on this device. There's nothing you can compute on this device that you can't compute with a classical supercomputer, or with a classical computer, even a laptop, right? This is trivial. But the tremendous impact this had was one, this is a very powerful research device. What really used to be the kind of work that someone could do in a very specialized academic group, now people could experiment with these devices, and access to devices like this has basically led to over 2,500 papers from the IBM group alone, from the IBM devices alone. And the other aspect was this became a very, very powerful computational tool, a very, very powerful educational tool, I'm sorry, right? So for students trying to learn quantum computation, this gave students the opportunity to actually experiment with these and see what one can do. And this is my colleague Antonio Corcoles, trying to program one of these things. This was one of the early interfaces with a drag drop menu, but you can basically see with a classical computer, you can just drag in operations. The operations are basically operations you apply on individual qubits, but also entangling operations. And then you can basically create sequences of these operations as you see in that in the tablet on his hand. And that's one way to program these systems. But now there are more accessible ways through Python interfaces and so on that you can really program a quantum computer the way you're familiar with in your regular programming. Okay.
I think you talked through this, so maybe I'll skip this. Yeah.
Okay. Yeah. Right. So I said in 2016, we had this first 5-qubit machine. It wasn't capable of doing anything that you couldn't do on a supercomputer or on a classical computer. In that period, in the last 6 or 7 years, we've begun to build increasingly powerful quantum processors. And while we're doing that, we've been able to build more powerful devices and have them accessible for users. Okay, and this is example of one recent result, which basically showed that even though these were extremely noisy, these devices, there are ways in which you can still perform accurate computations. Okay, even before you build this full error-corrected thing, there are ways to produce accurate computations from these noisy devices, and this is happening at the 127-qubit scale, right? Trying to represent the state exactly on a classical supercomputer is impossible. Okay, so this was one key milestone, to show that that even with noisy devices, it's possible to perform accurate computations. If we go to the next slide, and there've been very important milestones from other technologies as well. Anil alluded to many different flavors of qubits. Recently there was work with instead of using artificial atoms, you can actually use neutral atoms to build very complex devices, and we're beginning to see how one can use physical qubits to try and build some of the building blocks of these logical qubits that would lead to a fault-tolerant quantum computer in the future. Okay, and then there's another technology. This is from Quantinuum, which involves using trapped ion qubits. Once again, relies on more natural on nature-given quantum systems to use as qubits. And here again, the kind of error rates one is seeing, that they've gotten very competitive at a fairly large number now, at about 56. And they're also able to do computations that could be challenging for classical computers to simulate. Okay, so what's happened in the last few years is across different technologies, we're seeing increasingly complex hardware, and we're also across organizations giving people access to these systems where they can begin to run their own computations, right? And if you go to the next slide, if you just click once again, just across, the IBM quantum network alone, and I'm sure, all these different quantum hardware providers have a network of their own. There are a very large number of organizations in academia, governments, industry that are engaging, and they want to get along this path of trying to figure out how we can use these systems and what we can use them for. Okay, and I find that quite amazing that even as this technology matures, I mean, a lot of these have been research-grade devices, and there's just a vast community eager to engage. If you go to the next slide, and these are just examples of what a lot of our industry partners have been trying to do. JSR is trying to simulate some materials they're interested in. ExxonMobil as well. There are examples from the finance industry. So really the kind of applications people have been exploring, you'll see examples of machine learning algorithms trying being mapped onto quantum devices, optimization problems, quantum simulation, of course, and really all of these different organizations are, one, that they're trying to build their familiarity with these kinds of devices, and two, they're beginning to explore what are the problems that they struggle with in their day-to-day research or in their day-to-day work to simulate on classical supercomputers, and how does it match up when they try and map these onto quantum devices? And to give you a sense of the Indian industry ecosystem very quickly, there's been engagement in the context of the National Quantum Mission, with HCL, Tech Mahindra, and even TCS. TCS has recently announced a collaboration with IIT Bombay. That's more in the context of quantum sensing. But yeah, these are some headlines that I pulled up from press releases from the respective companies. But they're all really very interested in trying to make an impact in this field and build explore applications in different areas, banking, telecommunications, and trying to optimize manufacturing and so on. So there seems to be a lot of industry engagement across the world in trying to explore what those crucial applications would be. Okay, I think that's from me.
Good, Abhinav. Thanks. On that one, Anil, I wanted to kind of turn it over to you. As part of IIT Madras, you've been kind of the hub of a lot of the quantum computing work that's happening. Do you want to, putting you on the spot here a little bit, but talk a little bit about how you see the industry growing in terms of engagement with research institutions as well as industry and government?
I think with any new technology, actually, it's always the case of there are early adopters, and then there are those who sit on the fence, and then those who come in late. A little bit of FOMO happening in some industries. They don't want to miss out, and they jump in, and they do have the resources to start early research. Many industries are still watching and trying to see if there is some genuine quantum advantage that they can see in their respective businesses. So that balance, I think, is still being played out. We may be, people hesitant about too much of hype, and then you still don't want to postpone the training of your personnel so far that you are not competitive in the coming years. Right? So from an academic standpoint, what we have found is that, if we can do an upskilling program for people who are already in industry, that usually helps. They're currently employed, they wish to upskill themselves, learn new skills, they take certificate courses. That has been very popular. And we see a lot of that happening. We are conducting our second cohort, and, over 100 participants already. So I think industry is curious and also hesitant at the same time. And it differs from person to person. People who are already doing quantum chemistry, for example, might adopt it early on. But people are quite happy using GPUs and machine learning, do large language models, might just say, let me make my money today with GPUs, and we'll wait for the quantum to actually kick in. So I think that's what's going to happen.
Yeah, Anil,
It makes a lot of sense. Go ahead.
Sorry, one question again, coming from the industry, and I think I saw one of the questions on the Q&A blog also. What will be the impact of quantum computing on cybersecurity? That is the key word, as on what's happening in the last few weeks, what happened, all the cybersecurity issues are popping up, how that will make a difference.
Yeah, see, I think, that is the reason why a lot of governments are actually investing in this. But that is the hardest of the problems to solve. I think it's going to be at least another 10 years before we have that capability. But remember, there is this danger that everyone's aware of, that you could steal data in transit. So you have to decide what is the lifetime of your data. If your data is 25 years, then you need to start protecting it today. If your data is going to expire in 5 years, then okay, you take the risk. Right. Correct. So there are some areas, let us say, I'm building a submarine or something. I don't want my submarine plans to be out on the internet because somebody decided that, they should put it out there. So it depends on the lifetime of your data, right? I mean, completely. You could have Coke's secret, for example, I don't know, a secret recipe out on the internet, and you don't want it to be public for the next 50 years. I mean,
yeah.
So I think that's where the cybersecurity comes in, that we expect that we'll be able to sort of make the current way of doing public key encryption defunct. And so that is why NIST is putting out these things called post-quantum cryptography and so on. And people will adopt it because they expect at least 10 years of lifetime for their data.
Right.
Yeah,
That
so
makes sense.
Witty, what you mentioned and just adding on to it, there are a couple of slides. We won't spend too much time here, but exactly what Anil said, right? Maybe I'll alter one word Anil said, which is it's further out, but exactly what it is so just to clarify, because this used to be, as we talked about quantum computing over the last 10 years, this used to be one of those concerns that would come up is people were worried, right? Things would happen tomorrow and this would all break. So it's certainly not tomorrow. It could be over the next decade. It could be in the second decade after. But the key is exactly as Anil pointed out, to be ready today, given that you can harvest data, right? And there are many of these things that plan out 10, 20, 30 years in advance where you want to be able to protect that data today. And the nice part there is, so it's not quite quantum computing, but it's the fear of what quantum computing brings, as Anil, Abhinav was talking about Shor's algorithm, and how do you prepare for it today? And that's really what kind of it comes down to. This actively is probably happening today, harvesting now and decrypting later. And what do you do about it, right? For whatever comes in the future, whenever these quantum computers that are fault tolerant, they're available. So what do you do today, right? And that's what I think Anil referred to it. NIST has been talking about these algorithms that are actually implementable today. And so a lot of the work, certainly by IBM, but many others, is really educating governments, enterprises to start to figure out what would it take to start updating your security infrastructure with these new algorithms so that you are prepared. Right. So certainly IBM has hardware that's quantum safe. You'll hear the words post-quantum cryptography, you'll hear the words quantum safe. That's what it is. They're not really quantum computers, but they are getting ready for those highly performant quantum computers in the future. And so it's another field. I think, I said, this is probably the end of it, but in the slide deck today, but a lot of opportunities and things people can and probably should do today, given where the technology is headed and how it's accelerating.
Got it. Thank you. Yeah.
All right, so we're gonna go back. That's good. It's a good question. We kind of jumped in and answered. We're gonna start here, but I think we are almost to the top of the hour. So I think we're gonna try to. This is just more giving people a sense of who are the clients today, what are the kind of fundamental parts of quantum computing and what problems it can address. Who are the people? Fortune 500 companies, world leaders who are addressing it, as well as startups and research institutions. And what are the kind of problems that they're looking at, whether it's in materials, whether it's in math driven, whether it's in optimization. These we found working groups, but really it looks at how do you get a lot of these kind of world institutions together, universities, enterprises, and what are the broad topics that they are looking at, whether it's healthcare, whether it's materials, it's optimization, or it's in kind of physics-based. We wanted to spend some time, and I'm hoping Anil and Abhinav can jump in here too. The workforce development, right? So Madras is doing a fantastic job in India. IBM's trying to do the same thing here, and there are many institutions in the US who are doing the same as well as in Europe, right? Which is to get people to understand not only the basics in a lot more detail than what you heard today through tutorials, but also on how these are implemented, because the work really is being done by certain institutions on kind of the hardware level and the software stack on how people can access these systems. But a significant amount of work that's remaining is in algorithms and applying those algorithms to use cases. It's a completely open field where effectively people, not just physicists, but engineers, computer scientists, designers can jump in and participate. And really the work that's happening here, even down to high school level, you'll look at it and people have published huge documents on curriculum for quantum at the middle school, sixth, seventh, eighth grade level, at the ninth through 12th level, college level, as well as postgraduate. So there's just a lot of material out there, pretty much for free, right? IBM has a site out there. I'm advertising this here, but as I said, there are courses on edX by all the top universities across the world. Anil was talking about courses IIT Madras has. And then there are these, upskilling courses of, hey, if you're doing something today in the regular IT industry, how can you be part of the quantum computing industry? So an incredible amount of content out there that is just a simple search away that takes you from very basic fundamentals to everything beyond. I just listed some of the work here happening worldwide as IIT Madras is here, but how people are engaging students, leveraging content that's out there as well as resources that are out there. So just want to kind of give you a sense of what's really happening worldwide, that it's free, and if you want to learn more, you can jump in right away. The other part, this often has questions that have come up as we've talked to people, and there may be many people on the webinar today who are interested, is how they participate in the industry, right? So we've had a supply chain or an ecosystem out there for all kinds of computers that people build today. And computers as well as other components and devices. And the reality is there are certainly some unique components that can only be used in quantum computing, but there are a lot of component manufacturers who actually already have the building blocks of contributing to the quantum computing industry. And so part of this really is, and what IBM's been doing, along with many organizations, certainly within the US, but also within India and Europe, is organizations that bring industry uh, together with research institutions and quantum computing manufacturers, is to figure out what are the needs today, 3 years, 5 years, 10 years from now, and how they can participate, right? What are the specifications of some of these components that need to be, how are they going to be tested so they can be deployed in quantum computers? Quantum computing is at a point where today it's starting to do things that are useful, but it's going to get to a point where we're going to need many of these quantum computers in the cloud, and that's going to need an ecosystem and infrastructure built to be able to build these systems so people can use it. And just want to kind of give a flavor for what's out there. This is a chart, Anil, you and I were talking about. This was from the World Economic Forum from a couple of years ago, but it gives a sense of what countries in the world and regions in the world are investing in quantum computing, right? China kind of stands out, fairly significant number. Again, this is from 2022. I'm sure these numbers are larger now. And you'll see it. I think there are a lot of initiatives. Obviously, the National Quantum Initiative in India is big here. There are many countries in Europe, certainly individual countries, as well as the entire European infrastructure that's investing. Certainly in North America, there's a fairly significant interest, as well as in Australia and New Zealand. So you can kind of see it. The investment is quite significant. I think I didn't include those, but there are charts that talk about this number pretty much rising exponentially over the next many years, right? Especially from governments, right, where this is in supporting the ecosystem, supporting the research, supporting the hardware infrastructure, and then supporting all the work that has to happen in software as well to be able to do that. So this is certainly on the right track. I think the goal is to proceed and let the data take us rather than the marketing. And that's really the goal here, is to try and differentiate on what's hype and marketing versus what are actually demonstrations. And many of the things Abhinav talked about really tend towards that, which is really using data. What are people doing with it? What are people publishing? And I think the more demonstrations we see, the more convinced people will be. Wanted to talk a little bit about the future, but I think we want to give some time for Q&A. So just wanted, I'm going to run through this a little bit, but really to say what's coming. We'll certainly share the IBM roadmap, but the reality at this point in a timeline is many other firms have their own roadmaps that talk about getting to more performant quantum computers over the next 5 to 10 years, right? And that's something to kind of keep in mind as we do more, as we increase quality. That's really what's going to come up. I'm going to stop here. There is this concept of quantum-centric supercomputing, but I'll just stop right here to effectively say that it's really not standalone quantum computers that are going to solve all these problems. It's really quantum computers in conjunction with the other classical computers that we have today that are really what's going to solve some of the problems that we've talked about. So I'm going to stop right there. I think what we'd probably like to do is get into the questions, see what hasn't been answered by the presentation so far, and we want to pick those. So,
So
I've been
thanks.
trying to answer as many as I can.
So Anil,
as
Thank
quickly
you,
as I
Anil.
can.
you're
But they
getting a
come
great
really fast.
Anil, you're doing a great job. We had more than 80 questions, and I think half of them you have answered already online. But Rajeev, Abhinav, and Anil, I know some are very complicated. It can be taken offline, but some are like straightforward answers. I think so. So why don't Anil, Rajeev, and Abhinav, you look at the Q&A
Okay.
blog instead of
I'm
me
going through
repeating
that
it.
right now. So,
Yeah, please.
all right. So let's just go top to bottom here, right? And whoever has it, Anil and Abhinav, if you're ready, just go for it. I'm reading it for the first
Thank
time
you.
now that I've stopped sharing. So
Maybe I can address the question that came previously on integration with classical semiconductor-based systems.
Right.
Since we promised we'll get to that. Yeah. So there are many examples of how both could be used. There was one very interesting paper that came out from our own group actually just a few weeks ago on really extending the kind of molecular simulations one could do in conjunction with HPC. So having workloads that are run on a quantum device, but also then on a classical supercomputer. So that's one example. There are also many other ideas on how one can extend the depth of operations, so the number of operations that you want to run, by simulating perhaps one half of it on a quantum device and the other half on a classical HPC. This could be a much more accessible immediate path to quantum advantage. So I think this is going to be a very big thing in the next few years, and you'll see increasing numbers of organizations having quantum computers working very closely with classical HPC.
Great. Thank you.
Abhinav. All right. So I think there was a question on cybersecurity. Hopefully, we talked about that a little bit. The question on will quantum computing be used in daily government functioning anytime soon? So I think governments are certainly very interested. As I said, I think many of us said it is a lot of it is related to kind of this cybersecurity idea of what might happen in the future. But there is absolute interest I think you could imagine defense governments are interested in certain applications where it's either large scale problems, whether it's an optimization or certain machine learning ideas that in the future could leverage quantum computers. So I think there is certainly potential. The timing of when quantum computers will become useful to solve some of those large scale problems is probably further out. I think there was a question on, what are some of the fields that these would be applicable to? And I think, as Abhinav may have addressed it, some of those really related to chemistry, right? And quantum chemistry which is kind of the most obvious form where quantum computers can probably be helpful early, and that translates in real world to materials and so on. So I think, and batteries, as Abhinav talked about, those might be some of the early use cases that come through. But I would also say part of the reason we've engaged and other enterprises have engaged with everybody else who's providing quantum computers is to really map their problem sets to what quantum is good at, right? And that's why those engagements early matter, right? Anil was talking about the fact that some people are waiting on the sidelines, and that's perfectly fine, right? There is nothing a quantum computer can do today where people can make money off it, not yet, right? But the reality is, and it takes a while to take your problem, what do you want to solve, and figure out how well will you adapt it to what a quantum computer can do. We know, and I'm sure many on the call today know, even when people were moving their workloads from CPUs to GPUs, it took a while. It wasn't overnight. It wasn't immediate. And I think that same concept of using CPUs and GPUs today and how would QPUs solve that is going to take time for everybody. And I think it's really figuring out that mapping that helps. So,
Thank you.
okay. What else?
I think this question might be a good one. It'll be nice to know where India has its strengths, and it's a question addressed to Anil. So I'll let him answer that.
I get into trouble when I take these questions.
Do you want me to answer it then?
Yeah, why don't you go for it? Let's hear that.
Okay, sure. So I think it's good to compare the ecosystems and try and get some sense of what a very strong academic footprint enables for industry, right? So I think superconducting qubits is probably the most prevalent experimental technology in India right now. There are probably about four labs. There's one at the Tata Institute of Fundamental Research. There are a couple at IISc Bangalore. There's one at an institute in Kolkata, TCG Crest. And yeah, at IIT Bombay, there've been efforts to build quantum computers with semiconductors, spin qubits. That's ongoing work there. IISER Pune, I think, has an effort to build a trapped ion quantum computer. And yeah, I think I've covered the big players. There might be others have missed, but yeah. So there is an increasing footprint of experimental groups. Of course, I think on the algorithms and theory side, there's probably a lot more. But yeah, to give some more context, I think in superconducting qubits alone, I think in the US, one would at least have in academia about 30 research groups, right? And a lot of that ecosystem feeds into hiring for industry jobs, and yeah, so growing that academic ecosystem will also be important. Okay, cool.
I will say, so Anil, I'm going to punt it to you, but I'm going to say that isn't that a significant part of what the NQM and the various groups are trying to do, right? The goal really here is to attract proposals from, I don't know, I'm sure there were, you probably know the numbers, but there are tens, if not hundreds of proposals that came through. The teams are combining. So the hope is then to really balloon that, right?
Yeah, I think the National Quantum Mission is aiming to achieve that. we call it with those words very carefully, right? National Quantum Mission. And if we take it seriously and we do work together in a collaborative manner in a mission mode, we are hoping that we will have competitive advantages or strengths over the next 6 years. A lot of it is investment heavy, I think. That's also a part, right? And, we are playing catch up with similar efforts in other countries. But one is optimistic that it can be done. And you don't necessarily, there's an advantage to coming second always, right? I mean, you let the first person make all the mistakes. So we're hoping we don't have to make the mistakes that others did over the last 20 years and we can sort of catch up. But I think the levels of investment that are required are still very high. And that I think is always going to be a challenge for us.
And I honestly, this is maybe my opinion a little bit, and not even necessarily IBM's as such, but the fact that I think the work that's required in hardware that will continue, and exactly like Anil, you said, right? It's very capital intensive, a lot of investment. But the incredible amount of work that still remains on algorithms and being able to actually leverage these, pretty much everybody in the world's in a level playing field, right? So the opportunity there is where it's tremendous. So if you look at the software improvements that have to occur on the stack, as well as kind of how these are going to be used, pretty much everybody is starting off that way. And I think using what's already accessible can happen in parallel. And that's where I think advancement will go a long way too.
I just want to say something because this is often a topic. See, not everybody needs to become an expert on quantum mechanics and the qubit and so on. If you look at the full stack, right? I mean, there's a lot of electronics. I mean, it's like 99% of it is electronics engineering and microwave engineering and cryogenic engineering. And then you get to the software layers and you're sitting and doing firmware and different. And finally, today, everybody is a Python programmer. Because people like IBM have been successful in writing the high level thing and taking it down, you can just be a Python programmer and you don't really have to worry about all of that. But if it comes to algorithms, you do need to understand what you're doing. And I think that is where India has always been, has always benefited from very strong theory groups. HRI has a very large theory group, right? There are other theory groups also around the country, IIT Bombay, IIT Madras, ISC. So I think one has to do both. One has to understand is that today you can implement algorithms on hardware that is existing. And that will actually feed into a lot of employment opportunities for industry in India. But at the same time, you can also build the hardware, or you can attempt to build the hardware and sort of own some of the indigenous technologies that can develop while building that hardware. So I think both the National Quantum Mission is going to attempt to do all of it.
Yeah, very, very well said, Anil. I agree. Again, another plug, but I think you're finding that the abstraction of what you need to know about quantum mechanics to the point where you can actually start to program has come a long way. I think it has benefited from what was being done, assembly language, back in the 60s on classical computers. And now today, nobody really needs to know assembly language. And that's already kind of happened on the quantum side. So I think hopefully that can, that's a good analogy. Looking at some of the other presentation questions here, people talked about, I think there were a couple of questions on D-waves and circuits versus annealers. And I mean, maybe you can add one. I'm trying to look at time too, but at a very high level, what D-Wave has started, I think I would give them credit where I think they started the commercialization of the industry maybe 20 some years ago, maybe 15 years ago. So I think they get the credit for that. I think what people have realized is they are not quite universal quantum computers, that they are not able to really do a bunch of tasks. Anil had mentioned earlier, typically in logic, in gates, in classical computing, you can pull those gates together and really do anything you want on a classical computer. That's what many of today's quantum computers are mimicking is what they call universal quantum computers. You can really look at all these various tasks and different algorithms. There was a question, what are the other algorithms? Not Shores and Grovers, but there are many of these algorithms where you can implement using a universal quantum computer that you really cannot do with the D-Wave. Anil. The D-Wave, I think twice before I call it a quantum computer. But I won't go there. But the reality is that it does a very specific task. And I think that's the primary difference on D-Wave versus some of the others. And honestly, D-Wave themselves have recognized it, and they have an effort going on universal quantum computers. They just have a ways to go there. So anybody else see questions? I'm looking through it. Breakthroughs needed in software and infrastructure investment. I think we talked a little bit about it. Um, I think a lot of it is going to be how do you leverage these? There are existing algorithms, there are more algorithms needed. Abhinav is one of the world experts in how we leverage these algorithms to do useful work. I'm sure there's a lot more to do there. Even my simple mind talks about search algorithms have improved over the years, right? There are still innovations happening in classical computing algorithms over the last many years. And I think those kind of improvements will make quantum computers a lot more efficient and effective. So I believe there's a lot more to go there.
Maybe
Uh,
one question that typically gets asked at panels, which also has come up here. So I'll ask maybe both of you. Where do you expect quantum to be first commercially used? Do you have any guesses or opinions or?
I think Anil is going to go first in that one.
I'm going to say IBM is already using it commercially.
Okay.
Uh, yeah, my best guess would be it would have to do with chemistry and molecules.
Mhm.
Or, it could be a space which classical computers find hard to explore. That's one of the answers I put in there. You could think of, for example, a GAN, a generative adversarial network, that is trying to be used to train other generative AI models. And you'll find that the GANs have some problems because they're using a fixed training set. And if you can use a quantum GAN to explore a wider space, that could be a possibility. But these are really early days. We have no clue which one is going to win.
So in the interest of,
Yeah.
sorry,
Yeah,
Rajeev.
go ahead. Go ahead. No, that's go very. I
You
know
know,
we only have a few minutes remaining.
yeah,
So
I'm really excited. We still have 50 questions to answer, and we only have 7 minutes left. So I will request you, Rajeev, Anil, and Abhinav, just glance the question and see if you can give a consolidated response so that many of the questions are covered. That will be great in the next few minutes because once this webinar ends, we'll not be able to reply to
yeah.
these questions.
No, I've been looking at them. I think Anil maybe touched upon. I think there always comes this question on, hey, quantum and AI, what can we kind of pull together, large language models and so on. So I think the question of can large language models be run on quantum computers? I think probably the answer is no just yet. But there are certainly ways where quantum computers can help in training for in kind of machine learning. I think Anil may have just referred to that a little bit. I think it's still mainly in the paper space right now on how well can the two work. I think there's opportunity, but I think there's a lot of research that's needed. The
Actually,
opposite, though, is happening, right?
let
I
me
just mentioned one thing. Go ahead, Anil. Go ahead, and then I'll
Yeah.
mention the
So,
other.
there is this thing that even when you talk of papers, if I'm writing a paper on the advantage of doing quantum something, I don't do as good a job on doing it classically. To really get an apples to apples comparison, you need to take the best guy who can program a quantum computer and the best guy who can program a classical computer and pit them against each other. And I don't think anyone's done that yet. Right. And classical
Interesting.
computing is not standing still. So you really have to ask yourself, when is the crossover point between classical and quantum computing? right? Is it going to, and for what algorithm? So you might be very application specific in the near term. So if you have an application and you have a particular architecture and you have a particular algorithm, you may see some advantage. But will we see universal quantum computing beat universal classical computing anytime on all tasks? I don't think that will happen anytime soon.
Right. Yeah, no, that I agree with you. I think it's really going to be, and I'm sure it'll start off even to another way to answer Abhinav's question. It's going to start off as a trickle. There are going to be some very specific use cases that show benefit. There was a question out there on the financial industry, and I think that's how they are looking at it, right? Where fairly minor, what might seem like minor advantages over classical could be sufficient for some of the use cases that they're referring to. And I think it's going to be that where that's why the work is going on with enterprises is to figure out where can I get that even slight advantage. And I think it's going to be a combination of hardware improvements that occur over the next few years, advances in algorithms, and just integrating potential uses with those specific examples. So it's not that specific, but I think the advancement has been pretty significant. There were multiple questions on how can I access quantum computers. I see multiple people asking about it. Is it for free? Again, plugging for IBM because I know the IBM part really well. You can go on quantum.ibm.com, sign up for an account, and pretty much on our best systems out there, highest performance systems, you can get some time for free. So I would say I encourage people to go off and do it. A lot of students have done it. More than 500,000 users have done this over the last many years. So they're actually a fairly significant community. There are Slack channels out there that you can learn. There are many students who join those channels to learn about how to use a computer and what to do with it. So I would certainly encourage people to go do that. That's part of it is the community building, and there are events pretty much in all parts of the world that we organize, and as I said, others do as well, to be able to really build up expertise from people. So there was a question I see on classical people using classical computer science background, how can they pivot? And exactly like Anil mentioned, we've discussed it here, but it's I think can be reasonably seamless, I would say. The number of people, computer scientists who we get as interns, as regular hires is fairly significant, and everybody has a background in classical and can jump on to do programming quantum computers. All right, I'm going through it. Maybe I should have been clicking answer live here, but
So maybe
okay,
Rajiv,
yeah,
last question, and we have 2 minutes.
sure,
I'll just take the last minute to
go for it.
close the webinar. But no, I'll give you 30 seconds if you want to answer one more.
I'm looking through it, so please go ahead. Unless Abhinav and Anil see anything, I think we seem to have addressed many of these.
Excellent. So thank you. On behalf of PanIIT USA, I would like to thank my three panelists, Rajeev, Anil, and Abhinav, for a great webinar. 90 minutes went off, and you can see more than 300 people joining at one time, and a lot of questions, over 100 questions been asked. But that means that this topic was really very much needed to be covered in this webinar. So again, would like to thank Ron Gupta, President PanIIT USA, Swati Deshpande, she is our executive director, and all the volunteers, the board members of PanIIT USA who really support these initiatives. And there's a pro bono work, and we come forward and try to put these together. And we'll keep on doing this in the future also. Anybody who wants to learn more about PanIIT USA, please go on our website, iit.org. And if you have any specific questions, post it there. We'll try to answer those. Once again, thank you very much. Anything you would like to say, Rajeev, Anil, Abhinav, before we close this webinar?
No, I think I just want to thank the organizers themselves. I think it's always a pleasure to participate in some of these things, and the Q&A is always very active, which is a good thing because it's a new topic and people are curious. So I look forward to hearing more of these sessions from PanIIT.
Thank you. And before I forget, we'll be posting this presentation, and the recording will be available on YouTube. So we'll be working on that, and you can have this slide decks. It will be on our portal soon.
First of all, I would like to thank the speakers today. It's wonderful what you've done. I'd like to thank Witty for organizing it. Just wanted to encourage to work with the Government of India, Secretary of Science and Technology, Abhinav Kandala, who is previously was an IIT director, and is trying to infuse a lot of quality, a lot of quantum mechanics into his agency. So if you haven't worked with him, I'll encourage all of you to do that. Thank you again for such a wonderful program. Thank you for completing it within the time frame that was allocated for it. Thanks again.
All right, thank you. Thanks, everyone.
Thank you all.
Bye.
Thank you. Bye.
Thank you all.